In this module, you will learn about the Lenz's law. Before attempting to learn about Lenz's law, let us first recapitulate about the right-hand grip rule applied to a current-carrying coil. Consider a right-hand fist with the thumb extending out. If the fingers are wrapped in a circle pointing in the direction of the current through the coil, then the thumb points towards the end of the coil, indicating the north pole. Lenz's law helps us in identifying the polarity of the induced EMF in a coil. Lenz's law states that the polarity of induced EMF in a closed loop is such that it tends to produce a current which opposes the change in the magnetic flux that produces it. We can put this statement in simple terms. If a current is induced by an increasing flux, it will weaken the original flux. If a current is induced by a decreasing flux, it will strengthen the original flux. The magnitude of the induced EMF is given by Faraday's law, which is E is equal to minus d phi b divided by dt, where E is the induced EMF in the coil and phi b is the magnetic flux. The negative sign in this equation represents the effect as stated in Lenz's law. Let us look at Faraday's experiments and apply Lenz's law to them to identify the polarity of the induced EMF and the direction of induced current in the coil. In this experiment, the coil, which is connected to a galvanometer, is at rest. A bar magnet with its north pole facing the coil is moved towards the coil. This causes the magnetic flux through the coil to increase. A current is induced in the coil which opposes this increase in flux. The induced current is in a counterclockwise direction, looking from the bar magnet side. This current produces a north polarity towards the north pole of the magnet and opposes the motion of the magnet, thereby opposing the increase in magnetic flux through the coil. A force is required to move the magnet against this repelling force. The same magnet, when moved away from the stationary coil, causes the magnetic flux through the coil to decrease. A current is induced in the coil which opposes this decrease in flux. The induced current is in a clockwise direction looking from the bar magnet side. This current produces a south polarity towards the north pole of the receding magnet. This south pole attracts the north pole of the bar magnet, thereby resisting the motion of the magnet. When the south pole of the magnet is towards the coil and it is moved towards the coil, a south polarity is induced near the south pole of the magnet. When the same magnet is moved away from the coil, a north polarity is induced near the south pole. In all these experiments, we can also use an open circuit in the place of a closed loop. In this case too, an EMF is induced, but there is no induced current in the coil. The direction of this induced EMF can be found using Lenz's law. Here is an easy way to understand the direction of induced currents and EMF. We have so far taken Lenz's law for granted. Suppose that the induced current is in the direction opposite to the one given in the figure. In that case, the south pole due to the induced current will be near the approaching north pole of the magnet, causing the bar magnet to be attracted towards the coil. A gentle push on the magnet will start the process of motion, and its velocity and kinetic energy will continuously increase without expending any energy. If this is true, we can construct a perpetual motion machine with a suitable arrangement. This violates the law of conservation of energy and hence cannot happen. So, we can conclude that Lenz's law is correct. In all the experiments discussed, a force is required to move the magnet bar either towards or away from the coil. The product of the force and the distance moved gives the work done on the magnet. The work is done by spending some mechanical energy by the person conducting the experiment. The mechanical energy is converted to electrical energy in the coil. The electrical energy is converted into heat energy by heating up the coil, which is dissipated into the atmosphere. From these observations, we can say that the energy is only converted from one form to another, or the energy is conserved. You have now reached the end of this module. In this module, you have learnt that the polarity of induced EMF in a closed loop is such that it tends to produce a current which opposes the change in the magnetic flux that produces it.